rounding is, of course, the issue. And the usual way, and one typically thinks about rounding, is that you round to the nearest representable numbers.
Welcome to the wonderful and sometimes weird world of floating point numbers. And together with my guest Ulrich Ruede, who you've just heard, Andreas Herten and Edoardo di Napoli, we're going to dig a little bit deeper into what floating point numbers actually are and why it matters that we care about them. This is the second bite-sized episode of this season of Code for Thought, and floating points may be a bit of a weird subject to choose for a session. I mean, they're just basic data types, right? Every programming language has them, so why talk about them? Well, it turns out that there might be more to floating point numbers than meets the eye. About a year ago, I went to an online presentation run by the Grey Scott School in France, where Vincent Lafarge talked about, you guessed it, floating points. Vincent is a senior engineer working with high-performance computers at the National Research Centre in France, the CNRS. And in his excellent talk, he showed us all the horrible things that can go wrong if you don't take care when using floating point numbers in your calculations. Be that a guided missile exploding in the wrong location, causing considerable casualties and damage, or stock market values going down south. Helping me with getting to the bottom of floating points are three experts in the field: Professor Ulrich Ruede from the University of Erlangen-Nuernberg in Germany, incidentally where I started studying physics back in the days, and Andreas Herten and Edoardo di Napoli from the Research Centre in Juelich, also in Germany. First, I'd like to start with Ulrich Ruede, and we begin our conversation with a question of why floating points have recently become a hot subject again.
My name is Uli Ruede. I'm a professor of computer science at the University of Erlangen-Nuernberg. My field has been high-performance computing and numerical simulation. That means I'm trying to solve problems that originally come from physics and which are very compute-intensive so that they require more than just trivial compute equipment. And the range of things that I'm trying to solve is very large, typically engineering problems, but also physical problems, including helping with weather and climate simulations, for example.
Okay. And I think floating points play a certain important role in there. I thought that floating points is basically a closed chapter because there is, after all, the IEEE standard, 754, I believe. And people obviously talked about it in the past. It's an important subject, as we will discuss, no doubt. But why is it nowadays a subject again? Why are we still talking about floating points?
Well, the use of floating point numbers is, of course, still there because everything that is physical is in mathematics represented in real numbers, and floating points is the digital way of representing them with some limited precision. So that issue has always been around when it comes to technical computing. But as you say, rightfully, the IEEE standard is some 40 years old. I think they had a celebration that it's the 40th anniversary of that standard. And so probably until something like 10 or 15 years ago, many people like you would say, yeah, there is a standard, this is a solved problem and we can just go with it. Now, it turns out that some of the new hardware that we are getting, driven by artificial intelligence and partly also by computer games, visualization, image computing, requires less precision. And with less precision, you need less bits, and therefore you can build faster computers when you reduce the precision. So a lot of the hardware that we are currently getting, especially GPUs, offer much increased speed in computing, however, at the price of having significantly lower precision. And that forces us to look into that again, and it has become a quite hot research topic in the community again.
But maybe we're getting a little bit ahead of ourselves. We've been talking about floating points without actually explaining what they are. So maybe you can give us a quick rundown what a floating point actually is.
As I said, in physics, you have to deal with real numbers when you measure length, temperature, weight, whatever. These are real numbers, and the real numbers in principle are infinitely many, even uncountably infinitely many. And on any finite device that we can build to compute, we can only store a finite subset of that. And so the question comes up, which is the right subset of these infinitely many numbers that we want to store and to operate on? And this is exactly that floating point standard. And that means you have a finite precision and you have an exponent so that you can represent large numbers with the same relative precision as well as small numbers with the same relative precision. That is actually going back to the origins of computing. Even von Neumann was concerned with that. And then he was one of the first who discovered the consequences, which are round-off errors.
Apart from floating points, and this may sound like a silly question, but is there something like a fixed point?
Yes, of course. You can also work with fixed point numbers. This would then be essentially the integers. Also, there you have the issue that on a finite computer, you can only store a finite number of the infinitely many ones, but you still can simply count. And that means, if you have something like monetary tasks to compute, you have euros and cents or whatever, dollars and cents. And that would then be typically something with fixed point, where you typically don't want to talk for fractions of a penny or a cent. Then you're in the business of working with fixed point. Implicitly, you very often there include some rounding, like the commercial version of rounding when you maybe work with percentages of something.
Maybe at this stage it's a good moment to step into a little bit more detail about what floating point numbers actually are. So what kind of numbers do they represent on computers? Well, for integers, we have a fairly straightforward solution. Integers, whether they're positive or negative, can be represented in decimals, that is, in 10-base numbers, or, as is the case with our computers, in binary digits, bits. But integers are only, of course, a subset of all the numbers we have. There are the rational and irrational numbers, for instance, the number 1.5 or the number for the constant pi, an example for an irrational number. In short, numbers that contain fraction of an integer value, values that sometimes don't have an end even, like the value for pi or the decimal representation of the number 1/3. So in order to represent these numbers, computers have to do a little bit more work. The standard way of doing this is to split the number into 3 separate parts. One for the sign, indicating whether it's a negative or a positive value, then an exponent for the integer part of the number. For decimal values, this would be 10 to the power of the value of the exponent. And finally, the digits for the fraction of the integers, called the mantissa or sometimes called the significand. Let's do an example. The number 11.5, for instance. Using decimal notation, this can be rewritten as 1.15 times 10 to the power of 1. If we use the 3 parts I mentioned above, we have the sign, which in this case is positive, the exponent, which is 1, and the mantissa, which is 1/5. This, in a nutshell, is how floating point numbers are built on your computer, except, of course, instead of decimal numbers, the computer uses bits, binary digits. For a long while, the exact format of how these floating point numbers were defined and built was left to the manufacturers of computers, which, as computers became more and more widespread, caused, of course, a little bit of a headache. And so in 1985, the Institute of Electrical and Electronics Engineers, the IEEE, came up with a standardized version of how floating point numbers should be represented, the standard with the number 754. And according to its latest incarnation from the year 2019, yes, that means the standard is regularly updated, it defines floating point values using 32, 64, and 128 bits. For most computers and programming languages, indeed, floating points are represented with 32 and 64 bits. And in many programming languages, 32-bit floating point data types are simply called float, whereas the 64 bits are often called double. But 32 and 64 bits are not the only representations being used. In particular, with the rise of AI applications, a new type of floating point representation has emerged. And this brings me to my other guests, Andreas Herten and Edoardo di Napoli. And we start our conversation by going through the overall evolution of floating point representations over time.
Hi, my name is Andreas Herten. I'm working for Juelich Supercomputing Center at Forschungszentrum Juelich, Research Centre Juelich in Germany. And my main topic is supercomputing with GPUs and other accelerators. Yeah, we try to help people get onto the GPUs effectively and get most out of these devices.
Excellent. Thank you very much, Edoardo.
So my name is Edoardo di Napoli. I also work at the Juelich Supercomputing Center. I am a theoretical physicist by training, but in the middle of my career, I totally moved to something different. So I am a bit of a mixed bag by trade. I work a bit in the interface between quantum physics, applied math, and computer science. At the Juelich Supercomputing Center, I lead a small team of very specialized people that are really trying to support computational material scientists and quantum chemists to run their code as efficiently as possible on modern parallel supercomputers.
I find it interesting, as it's just a complete distraction now, that I think we're all physicists, aren't we? Because I think, Andreas, I remember that you're a physicist. Edoardo, you're a theoretical physicist, and I did experimental physics. But let's talk about the actual subject of today, which is how to represent real numbers with floating points or double. There are different types of floats and doubles, and there is a standard. There's the IEEE standard. Maybe we can touch on that a little bit later. But my first question really is, how did the format of floats and double evolve over the evolution of machines, in particular HPC? Andreas, maybe you can do that.
It has to do with how the processors have evolved and how we use these processors. There was a time, a long time ago, before I did all of this computing thing, when there weren't any standards. And it was a little bit of a wild west of how processors decided to represent numbers with transistors, in a sense. But then the field progressed, and then in the 80s, the IEEE made a push to standardize how you come from actual real numbers over bits to transistors. And they came up with this IEEE 754 standard, in which is basically defined how many bits are used to represent what kind of number. But of course, you have only finite set of bits available. So there need to be some rules on how you transform between bits and actual real numbers. And they come up in the standard how this should be done. And basically the trick, which is now used everywhere, it's the standard, and you have probably heard this, is to separate available bits into a set which is used for an exponent and which is used for a mantissa, or also called a fraction. And then there is also a bit to show in if we are greater than 0 or lower than 0. So that's the sign bit. And the exponent and the fraction, they are basically for telling where on the spectrum a certain number is located and to what precision we can represent this. So let's start with the fraction, the mantissa. That is basically a set of bits which represent a number to tell what a certain value is like and how we can understand it. But it's always, let's say, close to 1. And then in order to move it maybe to larger values, we use then the exponent to shift it away from this close to 1 location. So basically through this separation, we can represent any kind of number within the spectrum which is available to a certain precision which is available. And what is available is then regulated or standardized in this IEEE standard, because you can imagine if you throw more bits onto a thing, it will be either more precise or it can cover a larger range. Here, the standard is either a normal float, which we also call single precision, because it has in total 32 bits available, which are then separated into this mantissa and exponent parts. But then there is also formats available with less bits or with more bits. So maybe the most important, most famous one is the double precision, where you have 64 bits available. And of course, in scientific computing, where we come from, double precision in a sense is the gold standard, because it gives you a lot of precision for your algorithms, where usually in many cases it's important to reduce the error in your calculations because you're converging to a certain number, because you're kind of simulating how heat flows. And then of course at some point you expect that this will normalize and come to a certain state which you expect, and for this you need to also have a certain precision. And for this, double precision has established as the gold standard. And this was also then incorporated in the processors in the last years, or maybe in the last decades even. But of course, it comes at a cost, because having these 64 bits in hardware is also space intensive. You need to always the transistors to represent the bits into the hardware. And if you go to the best precision with this double precision, of course, you need to also incorporate at all times these 64 bits in any case where you need it, in all the floating point units, in memory, etc. But then people started looking, maybe a little bit going back to the roots, how it used to be, lower precisions. If not some of the algorithms which we are using also can deal with lower precisions, like this single precision of 32 bits, or maybe even 16 bits, half of this, or even half of that one again. So there is a trend to look at these lower precision algorithms, because of course they are less space intensive. So for the same processor design, which needs to incorporate a lot of bits to represent 64 bits, you can actually do much more at lower precision. So you gain performance, or you gain more capacity for more numbers, in a sense. Yeah, this is how everything came to be. So now we are in a world where I would say the gold standard is still 64 bits. Also the case for your personal computer, also for scientific computing. And there is people who are testing their rotors with lower precisions. And of course, the trend is fueled a lot by AI, because AI computing, which is driving a lot of hardware sales at the moment, they don't need the 64-bit to have their simulations or their trainings, in this case, converge. So they can make do with lower precision. And that means they can have more throughput if they go to lower precision. And that is why a lot of the processors which we have today, that are especially GPUs, invest a lot of silicon, a lot of transistors, in order to include lower precision computing entities onto their devices, and they gain a lot of performance.
Okay, we already mentioned that floating points are typically represented as 32-bit values, often simply called float, and 64-bit, sometimes called double, for instance in the C and C++ programming languages. And in scientific applications, as Andreas just said, using double seems to be the standard. But, as you heard, there's a trend to go to lower precision floating points. And there are a few reasons why that is, which is what I discussed with Andreas and Edoardo next. Well, thank you very much for that whirlwind tour through floating points. It's very good. I think it's also important to point out, going back to the standard a little bit, that each real number is represented as 1 point, and then whatever comes after the decimal point, so that you actually do not have to represent the 1 in the bits. So that's always omitted. So no matter what the real number actually is, it's always a representation as in 1 point, blah, 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 times 10 to the x.
Yeah, in a sense, yes. Yeah.
But going back to the format itself, so we have a variety of different formats. So we have the 32 and the 64 bits. Isn't there also a representation that goes a little bit higher than 64 bits on some machines?
There is also this representation for 128 bits, but I think it's not really realized in hardware. I would need to look at it more closely, but this has no hardware acceleration for all the chips we are using, which are kind of commodity or specialized commodity hardware. So it doesn't really play a role. But of course, it is standardized, so you could create a chip with it.
So in terms of performance, you explained to the listeners that the higher or the bigger the representation of a real number is in terms of floating point, a double number, it also means a hit on performance.
Exactly. So this comes from the fact that you just need more bits, right? So maybe it's too simplified, but think of it as cars, which you need to drive on the road, right? So you need to send the bits, which are representing a 64-bit number. So you need to send 64 bits to some certain address. It's just a lot of bits you need to send around. And of course, in a processor, which is optimized to reduce latency, to increase throughput, depending on the processor design. But in any case, you need to move around a lot of data. And then you also need to access a lot of bits in order to compute new numbers, maybe of 2 of these 64-bit data points. Then also here, you need to put a lot of these bits through your data path or your computation path. And all of this just is taking a certain amount of time. And if you can avoid it, it's always a good idea to do this.
I would like to return to the representation with lower bits or with fewer bits. So we talked about 8-bit representation or 16-bit representation. I think there are also 4-bit representations. So you're losing, obviously, a lot of precision. Edoardo, I think you're working on, you're the theorist amongst us. So how do you actually deal with that? Because you're losing precisions and, you're probably increasing the risk of rounding errors and all the other bits. How can you actually do proper math, shall we say, with lower bits?
Before I answer your question, I wanted to make a small historical remark that perhaps can also simplify the idea of the performance. If anybody can go back to the early 90s, when the 86 architecture came out, you may remember that there was the processor and there was the coprocessor. At the time, the coprocessor was not a graphical card, obviously, but the processor could do only very, very simple operation, but could not handle floats. And we need a coprocessor to actually do computing with floats. And that later on, this was included in the CPU, and we didn't talk anymore about coprocessor. I'm making this remark to make it easier to understand why, when you go down in precision, you can execute more calculations. Particularly the units that you're using are simpler and they can do more computation than when you're using higher precision. But going back to linear algebra, which is a bit at the base of a lot of calculations. So, and perhaps here a good point to start is to, again, going back to the example of AI. So in AI, most of the computation that they do are based on linear algebra. They do very, very small matrix vector multiplications. So you imagine, but these matrices are small, or the order of, a few dozens perhaps. And they do a lot of those, but they don't need a lot of precision at all. In the end, they always need perhaps 2-3 digits precisions. That's all they need in terms of extracting the results from these machine learning machinery. GPUs are very good at doing that. The vendor market focused a lot in that direction. But not all application can make use of such a low accuracy. For instance, in the field that I cater the most, the material science, actually higher precision is very often in need. So they cannot rely, not even sometimes on single precision, on 32 bits. They really have to go to double. Otherwise, they cannot distinguish between different solutions. Maybe for the audience to exemplify, they look at energy values, and these energy values for the lower lying state in a quantum system, they can be very close to each other, meaning to distinguish two different energy values, they really have to go to 10, 12 digits. Otherwise, they look similar, to look the same.
Yeah.
So in that case, going below double precision won't work. On the other hand, because now double floating point operations are the golden standards, many applications didn't really explore enough if they may reduce accuracy and still get their software working fine and converge. Because of the trend in GPU computing nowadays, more and more applications are exploring, and linear algebra is one of them. There are algorithms that may not converge in single precision or even in half precision because perhaps the operators are ill-conditioned, meaning these operators have the spectrum at the range so wide that you need a lot of accuracy to describe it. But there are cases where the operators are very good conditioned, and then you don't need such a large accuracy and you still converge fine.
What you're saying is that double precision is still the golden standard, but there are ways where you can actually achieve the same level of precision, but with a lower bit representation. Is that it?
No, I wasn't exactly saying that. I was saying that, so depending on the problem you're tackling, you may use different precision. What you're talking about is emulation, which is a different thing. Emulation is trying to express quantities in higher precision using a lower precision representation.
I've heard about, or you actually introduced me to the Ozaki scheme, I believe. Is that falling into that category?
Correct, yeah.
Could you explain what that is?
Yeah, the Ozaki scheme came exactly from this need, right? So from the fact that there is this trend in GPU computing where the computing units on modern GPUs are getting less and less flops for double precision and more for much lower precision. And so the trend in Japan is to plan ahead well in advance. And they are very good at that. So they really look at what can they extract from the next generation biggest machine that they can build. And so every time they move from one supercomputer to the next, and usually this span an interval of 10 years, they always want to get a 100 more performance, 100 times more performance for a new machine.
Right.
And so they observe that at the next machine that should come in 2030, they cannot do that with the current GPU evolution. And so they look into other ways to get there, exploiting the emphasis on lower precision on GPUs and still getting a precision they desire. So this Ozaki scheme, that's where they came from. Actually, there are two schemes. The first one is a simpler scheme where they translate a matrix on matrix-matrix multiplication, which is the golden standard of linear algebra. And they express these matrices in integers. And then they do this multiplication, they do a truncation, an accumulation, and back to trying to emulate higher precision. The Ozaki scheme 2 actually is even more clever. It uses something called Chinese reminder theorem. It's a complicated theorem, actually, and in China it's not known as Chinese reminder, by the way. But it's a clever scheme where practically they use integer 8 numbers up to 256, and then they select a subset of these numbers called coprime numbers. You can look at them or think of them as a reduced base. And then they try to represent any integer to this reduced base. Of course, they lose a little bit of precision, but they can make computations really fast using this integer 8 base.
It might seem a little bit odd at first to see machines getting bigger and bigger all the time and more powerful, while at the same time we're trying to downsize the precision of floating points. You might think with bigger machines we get even more precision. And that's a point I made in the final part of my chat with Andreas and Edoardo. Now we're talking about floating points and floating point representations, which is maybe a little bit counterintuitive now that the machines are getting bigger, that we're talking also not only about floating points again, but also about lower precision. So it feels like going backwards a little bit, doesn't it?
It feels like it maybe, but I think it's on a higher level or on a more advanced level now. So we have all the capacity to do it in high precision, but now we are consciously choosing lower precision because it gives us more benefits, right? But I do see the trend that the computing field will be more heterogeneous in this regard. So I think there was a time when you had no choice. Do either not 64-bit computing or emulate it somehow. And then there was a time when 64-bit was just the standard and no one really thought too much about it. And now we have the time that we do have 64-bit, but it's actually you are getting some benefits in sense of you can do more computing if you go to lower precision. And then the future, I think, will be that there will be even more incentives to go to lower precision or mixed precision or emulated precision. And it will become one more dimension of research to find out not only if your scientific algorithm which you're implementing is good and does produce the right results, but also if you can do this with lower precision or clever emulations. I think as long as there is a benefit and as long as AI is driving a lot of hardware sales, we'll have this. It makes sense because it's giving you more performance. It is a little bit more work to implement it and to test it and to evaluate it, but then you can reap some benefits, I think.
Edoardo, how do you see the libraries like BLAST, for instance? There are different implementations, I understand, but how do you see them evolve?
The trend until very recently has been always looking at double precision. Some libraries would have kernels implemented in double or in single, but no more than that. I would say some libraries have already been templating, meaning you don't need to specifically write your program that is tuned up for single or double, but you can invoke at runtime which one you want. I think the newest standard for C++ next year will also include linear algebra in it, like BLAST automatically and in a templated manner. I see the trend of libraries going somewhat in the same direction as Andreas saying about the hardware. The AI pushed the limits and indicated that there are other options. AI, as with everything in computing, now is driving a lot of development, but at one point it will perhaps be not the only driver and something else will come up. But the door is open now. And I think libraries will have to include and adapt. This means also there will be, of course, an extra effort at the beginning, but also an effort to try to provide a library with many different backend kernels. What I mean with that is that For each operation, you have different methods under the hood, and the user doesn't have to be specifically aware or know how they work. As long as the type of data is passed in a certain format, automatically the library will choose the kernel that fits better with the type of data and the accuracy of the data. I see this as a natural trend.
I want to use the last part of this episode to discuss some of the problems that you might face when using floating point numbers. And to warm us up for it, let's go back to my chat with Ulrich Ruede, where we touch on one particular aspect of problem, that of rounding floating points. Ultimately, when it comes to the limited number of bits you can use to represent a real number, you end up rounding, don't you? Like the number pi, for instance, to represent, ultimately it's an infinite number, but you only have so many bits to represent it in. How do you cut it off?
Rounding is, of course, the issue. And the usual way, and one typically thinks about rounding, is that you round to the nearest representable number. So you have this finite set of numbers that you can represent, and the one that you typically want to have is the one that is closest to the pi or even square root of 2. So if you want to compute the length of a diagonal in a square, you get square root of 2, and even that cannot be represented exactly. So you have this rounding to nearest, and that is actually the principle that is behind the IEEE standard. It is configurable, so you could also round to the next larger number or to the next smaller number. And actually, one of the topics is now stochastic rounding, where some of the algorithms tend to work better if you round not in a deterministic way, but you add some stochasticity to that, which can in some cases even get better results than rounding to nearest.
Well, in my past as a developer, I had some issues with rounding errors and other errors. If you're aware that these numbers are ultimately have a finite representation, then you end up with the question of rounding errors. There are other errors that may happen as well, and sometimes leading to catastrophic results. But as a developer, how can I actually take care of that? What can I do to at least mitigate the risk of too many errors creeping in?
This is kind of the question that leads into the job market for people who are experts on that. And my answer is that unfortunately, or if you're looking for a job in that field, fortunately, there is no unique answer. This, if you do, you're always safe.
Yeah.
There is nothing that saves you from, at least for your field of application, to know a little bit of the effects and be aware of them. And find the right cure if you have that problem, and the right cure may be different in the different cases. I think one of the fundamental things one needs to be aware of, that we typically think of round of errors, say if you take two decimal numbers, you multiply them together, typically you get twice as many decimal digits, and if you cannot represent them, you have to round. This is a classical round of error that you typically have in mind, and I think everybody is aware of. But the problem actually starts earlier, because if you have physical quantities, they are typically not precise. You've brought up the issue with even numbers like pi, which you cannot and never represent with infinite precision. But this is much more severe when you talk about something physical. Typical, when you have anything that is being measured by a device, it has some error in it. And that is typically actually larger than the rounding errors that you would get. And so the question of finite precision even starts in engineering when you set up your problem. If you build a bridge, there are materials, concrete involved, steel involved, and you will not know the material parameters with infinite precision. And so you have to be aware of that all the calculations you do are only valid up to the precision that you have the data. And on top of that come the rounding errors.
So I think one of the things that you can do to help avoid, well, not avoid errors, because ultimately what you're saying is there will be inherent rounding errors because, of the limited number of bits you have to represent a number. But I think the first step is to actually be aware of it, isn't it?
Exactly.
So,
this is what I'm saying. You need to be aware of, and that if there is such a problem, it may help to increase your accuracy. Say if you have been working with single precision, you can increase it to double precision, and that may help to get rid of your problem, but it may also not help. It may not be sufficient. And the bottom line is, for every precision that you give me, be it 32-bit, 64-bit, 128, whatever you name, I can get a problem which will break it.
Indeed, because the number of problems is infinite too.
Yeah, but I can just set up a problem that is so bad, and this badness is determined by a parameter that whatever you tell me, I make that parameter a little bit bigger, and you will again be in trouble.
When it comes to understanding what computers do with floating point numbers, there are two papers that you can't miss reading. The one is by David Goldberg, titled What Every Computer Scientist Should Know About Floating Point Arithmetic, which has become a classic discussing this. The other is by Vincent Lafarge, who I mentioned at the beginning, where he revisits the Goldberg paper, giving some concrete examples and advice on how to deal with floating point numbers in some example algorithms. The most common issue is that floating points are always rounded when a number cannot be represented fully with the number of bits available. The rounding error can be expressed with a quantity that's called ULP, which stands for unit in the last place or unit of least precision. So what on earth is an ULP? Well, it's essentially the difference between two consecutive floating point numbers or the value of the least significant bit of the value 1. In the IEEE standard, the rounding error should be within half of that value of an ULP. The end result is that the value of the floating point number is often not the exact value of the number it's meant to represent, and this can lead to rather odd behavior, one of which is called a catastrophic cancellation. And this is particularly pertinent, for instance, if you subtract two numbers which are very close to each other, but each of which is rounded. And there is in fact a Wikipedia page on catastrophic cancellations that has a very good example of this. Vincent Lafarge also has a few examples in his paper on revisiting the article by David Goldberg and giving us some recipes on how to get around or at least minimize these rounding issues. And I really encourage you to study these two papers, and you'll find the links in the show notes as per usual. As we said a few times already, rounding errors are inherent to floating point number representations, but sometimes rounding errors can be avoided if we as engineers take care. A classic example of that is data type conversions. And during my time as an engineer, I encountered quite a few of that. So it would go typically like this. You have a data type defined as a float, and then at some stage somewhere else in the program, the type gets converted to a data type of int, an integer. And then maybe later on it will get converted back into a float or a double. If this is a complex and complicated program or application with many different functions and classes, it may actually be quite tricky to spot this. In short, it actually pays to pay a little attention to the data type you use and the definition of them. But also I think we should mention that rounding errors may not always cause problems, which is why for some machine learning and AI applications the trend is to go to lower precision, as we heard. Again, this means to think about, as an engineer, what data type you'd be using. Does it always have to be a double, or can you get away with single or perhaps even half precision? So we're coming to the end of this rather long episode now, and I hope I haven't lost you on the way, but there's just one more thing I'd like you to do. In the show notes, you'll find a link to a website that converts real numbers into hexadecimal or binary digits. The tool is called IEEE-754 Floating Point Converter. It's a fun tool, I think, and have a little play around with numbers. For instance, what does happen when you use the number 0.1? What does it look like in bits? And is there a separate value for -0 and +0? As a second exercise, try to see if you can visualize the actual value of 0.1 with a Python programming language. And finally, also in Python, if you add 0.1 and 0.2, it should of course give 0.3. So if you ask, is 0.1 plus 0.2 the same as 0.3, the code should return true, right? Okay, I hope you have some fun with these exercises, and I hope that this episode made floating points a little bit clearer. Next week, we're going to have a German language episode, breaking with my usual habit of having them on the last Tuesday of the month. And in this episode, I'll be talking to the people behind the ALPS 2 experiment at DESY in Hamburg. ALPS stands for Any Light Particle Search, where the team essentially tries to shine a light through a wall in search for dark particles. Needless to say, there's a lot of exciting software and data analysis going on as well, so stay tuned. And finally, this episode is part of the ByteSized program run by the Step Up project in the UK, and I thank them very much for supporting this show. Thanks for listening. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.